People in here are thinking pre-professional largely in medicine or dentistry, and the allied health professions or professions that are working with them. And so it's good to think about those. Sometimes people think they want to be a physician when the actual jobs they want are not the jobs of the physician, somebody else. So that's why I have them come in and give their spiel so you can have that to think about. And this thing was in presentation mode a second ago. We're going to finish up with 2 quick slides and then move on to material that is from Chapter 6. So the 2 quick slides. Number 1, turn off some lights so you can see my fainter print there. Real life versus general physics for a falling object. So here I have 2 falling objects. One that's in a nice form to decrease his air resistance so he can really fly through the air. One that's more spread eagle to slow down. And when you have an object that's moving relatively quickly, we find that the drag force, the force of air resistance, is proportional to how fast they're traveling through the air squared. Now this would also apply if you were going through a liquid like water, any fluid, anything that flows. You would have one of these 2 relations. For higher speeds or larger objects, you have the force drag is 1/2. You might ask, why is there a 1/2 when there is this constant c that's experimentally determined for the object? That c is based on things like, its shape, how big it is, and so on. It seems funny to have a 1/2 factor in there, but we do. Rho is the density. This is the Greek letter rho. That's an R in Greek. When I was in graduate school, I had a classmate who was Greek, and she's going through equations, and circumference of a circle is is pi times diameter. And she said it's PD. And I'm all, PD? No, it's not P. But of course, that symbol there that looks to us like a P is an R in Greek. It's the rho. So rho is the density of the air. A is the cross-sectional area, and V, the speed. And when you have somebody in that aerodynamic form, their C is about 0.7. Whereas if you have spread eagle, it's closer to 1. So you're going to have more drag in that spread eagle form than you are going to have if you are in the aerodynamic form. Which form you're in, and of course you could be somewhere in between, is going to make your speed vary. Because as you're falling, what forces are acting on you? Let's draw the forces acting on this young lady on the right. What forces do we have? We have a force of gravity. And how big is that force of gravity? Just simple, just mg. Right? It's going down, has a magnitude of mg. And then we have the force that we have been ignoring and that we will continue to ignore unless specifically asked about it. But that's going to be the drag force, which is going to be 1/2 c rho a v squared. So taking those and using Newton's second law in the vertical direction, some of the forces in the vertical direction, I'll put my little indicator for y, so it makes sense to put some forces y, is equal to mass times acceleration in the y direction. Looking at the picture, going up I had force drag, going down I had the force of gravity. Now, if force drag is not equal to force of gravity, what's going to happen? If the 2 forces don't add up to 0, what's going to happen? We'll have an acceleration. So when she drops out of the airplane, or let's make it simpler, when she just lets her body fall over the edge of a bridge, right, to make it so I don't have to have an airplane involved, then initially her speed is approximately 0, so the drag force is approximately 0. Her net force is going to be downward due to gravity, and she'll have then an acceleration downward. But the faster she goes, the bigger this drag force upward is. And so if the drag force gets bigger, her net force gets smaller, her acceleration gets smaller, until she reaches a speed where the drag force is equal to the force of gravity and acceleration is 0. If the acceleration is 0, how's the speed going to change? Very trivial question. It does not change. So then she'll stay at a constant speed, and we'll call that her terminal velocity. So in real life, if you fall out of an airplane without a parachute, you are going to reach a terminal velocity, a final speed. If you go ahead and form your body into a nice little javelin shape and aim for the ground, you'll get up to about 200 miles an hour. If you go spread eagle and try to slow yourself down, maybe play a little gangster and loosen your pants up and pull them down so you get a little more drag, then you can have a terminal velocity that's in the ballpark of 120 miles an hour. That's better. 120 miles per hour, everything being ideal, you might survive. There are cases where people have fallen out of airplanes way up there and survived. Not very common, obviously. But that's because in real life we do have a very significant force from air resistance. It's a lot more significant if you're going faster. So now let's imagine you're in a space shuttle. I know none of you were alive when the first space shuttle went up. But we as Americans were petrified it was going to burn up when it came back because it was going to come really fast into the Earth's atmosphere. And so they had these big ceramic tiles that they put on there to keep the heat generated from hitting that air from getting into the space shuttle and making it burn up. Then it landed safely. Hurrah! The big sigh of relief. Well, at least I had a big sigh of relief. And then we found that a bunch of those tiles had actually fallen off, which makes it shocking that it didn't burn up. So that's a very real thing that has to be something we are concerned about. The textbook points out in automobiles at highway speeds, more than half of your power has to go into simply overcoming the air resistance of the car. And so making your car more aerodynamic is one quick way of making it have a better fuel efficiency. So car designers try to make their cars as aerodynamic as they can. And anything you can do to make it more aerodynamic, like if there's a hailstorm, parking it outside so you make sure you get the divots on the car, that will improve your gas mileage. Right? So it's kind of like a win-win situation. You get your insurance money for the hail damage and you get better fuel economy. Right? I know, none of us want that, but it's the bright side you can look at. All right, enough on that slide. I said we have two. The other one is on stress and strain. Elastoplastic behavior. Elasticity is the behavior that if I take something and deform it, it will come back to its original positioning. So, for instance, this right here. I can deform it, right? I bent it, I deformed it. I let go and it comes right back. That's elasticity. We have other things we use that are elastic, like my slinky here, which is basically a spring. I can stretch it, but I let go and it just comes back to where it started. That's elasticity. And all materials, if you just bend them a little, are going to have some elasticity. Our textbook says that if you have a deformation that's less than 0.1%, almost every material will come back. If you deform it too much, it will plastically deform. It will permanently deform. And so when we talk about stress and strain, we in a general physics class focus on the elastic portion of the behavior. If you're an engineer, you might look a little at the plastic deformation, but keep in mind, you make a bridge, if that bridge plastically deforms, it's never going to come back to where it was. You generally don't want that. You want it to come back. So even engineers are often working in that elastic region, but you have to determine how long materials are elastic and what happens. In our textbook, we have graphs that show things about the stress and strain. Now I have some words here. Stress. It's very funny, I think, to say, yes, stress is that thing you feel when you've got the test coming up, right? It's a relevant but not correct definition for physics. In physics, stress is very simple. Stress is the force divided by the area on which it's applied. So, force divided by area. It's actually a tensor. Chad's not here today, or I'd point him out and say, Chad, what's a tensor? I think he has more math than anyone else. I could be wrong. Anybody here know what a tensor is? Okay, I had no audible answer. A tensor is like a vector, but it has more dimensions. So the simplest tensors that we use are the stress tensor, which is a 3x3 matrix. A vector just had 3 values, right? X component, Y component, and a Z component for 3-dimensional space. The tensor has a total of 9 values, although it's only 6 unique values. Why is that? Because your stress can be compressive. That is, the force can be into the surface. If I take my hand and I push it down on the tabletop, the force is going into the surface, and that's a compressive stress. If I were to take my hand and glue it to the tabletop, I could pull it up, and then I would have what we call a tensile stress. When you have the force coming out of the surface, that's a tensile stress. And the third one, that's the main one, I said there's 6. There are 3 on axis and 3 off axis. The third one, if I glued my hand to this and I pulled it sideways, then the force is parallel to the surface, and we call that a shear stress. Things tend to be a lot weaker in shear than in the others. So we have 3 different types of stress, both compressive and tensile stress, the 2 that are shown here. Which one is this one here? That's compressive because the force is going into the surface. And so this one here is tensile because it's putting it in tension. And a shear would have had the force going like that. The tensile and compressive stresses can both be related to strain the same way. Of course, what is strain? If you were to use a standard student who's never taken physics definition for strain, you come up with something like, you grunt and strain, so it's how hard you push, or something like that. Well, for physics, once again, strain has a very specific definition. Strain is the deformation divided by the initial size. So strain is the change in length, whether elongated or was compressed, it's still going to be the change in length, it's just positive versus negative, divided by the original length. And those 2 are related through this thing that we call the elastic modulus. The elastic modulus is called Young's modulus as well. Modulus. You can't read my writing. You probably can't tell what letter I'm trying to correct. Modulus. Okay. Young's modulus, also known as the elastic modulus, so you'll see it written both ways. Might know. We use the E for the symbol if we call it elastic modulus, Y for the symbol if we call it Young's modulus, but it's the same thing. So E and Y are the same. It's just some tables will have one, some will have the other. That applies for both tensile or compressive stresses. So Young's modulus is a number to relate the stress to the strain. That is, if you put this much compression on it, it's going to deform this amount. That's what the Young's modulus tells you. Now notice our symbol sigma. That's of course an S in Greek for stress. Strain is an epsilon. I don't know why that's chosen, so I can't give you a reason to help you remember that one. And so the stress is equal to Young's modulus times the strain. Now, if you were to take these definitions up here and substitute them, and solve this for force, you have force is equal to this constant, Young's modulus times the area divided by the original length times the change in length. That equation should have a familiar look to it because it's the same as the equation we had for the force of a spring. We had for a spring, the force of the spring was equal to K delta X. And remember, there's a minus sign because of direction that I put in there when I put vector signs. But you can see the spring's equation is just showing that it's having elastic behavior. And so that spring constant K, we can now define, if it was something that was shaped like a cylinder, it'd be kind of easy. K would be Young's modulus times the cross-sectional area of the cylinder divided by the length of the cylinder. So that's the basics of what's happening with elastoplastic behavior. Now, if you put too much stress on something, if you make a graph and you put the stress here and the strain here, you should have what looks like a straight line as long as it's acting as an elastic material. But once it loses elasticity, once you put too much stress on it, then it will start to stretch more than you anticipated. So when you get past what we call the elastic limit, and yeah, my PhD work had to do with going past the elastic limit, this will start to bend over like this, and it'll stretch more as you increase the force. And then a typical material, and I'm not sure what they have plotted in the book because their graph didn't look like this, but a typical material, when you get it overstressed, then it just starts going out of control and starts stretching more. You can even let up on the stress, and it's still going to stretch more until it breaks. And so that X is where it breaks. So for these materials, you have an ultimate strength. The textbook has a different word for it, as well as the elastic limit. The elastic limit is how long it will behave as normal. The ultimate strength is how much stress you put on before it actually breaks. And that's almost all we're going to have on this. Only two more things. We talked about the different types of stress. You have a shear modulus that the equation looks exactly like my elastic equation, except for you put a capital S instead of a capital Y, because you have a different modulus for shear. That is, if I have something like this and I put a force like that on it, it's going to have a different modulus than if I had force going into it or out of it. But otherwise it looks the same. If you have a fluid, something that flows, you technically don't have stress. Something that flows, like air. We have air pressure, not air stress. Pressure is also force divided by area. The difference between pressure and stress is that stress can be different along different axes. Pressure is the same in all directions. So air pressure is just pushing in on us. So air pressure is pushing down the top of my head, pushing in on the sides of my head, pushing up on my jaw to try to keep my mouth shut, right? It's pushing up on the bottoms of my shoes. There is air that goes under my shoes and pushes me up. So I'm being buoyed up by that air pressure. If I was able to pull all of the air out from between my shoes and the floor, I wouldn't be able to walk anymore, because that would require too much force to pull them away. And that's the basis of how a suction cup works, is you lower the pressure underneath that suction cup. You have the air pressure pushing it in and nothing pushing it out, and it's stuck there. All right, now moving on to what, well, I think is more fun. Oh, I should check. I never checked to make sure my record was correct. I have here that Chad and Amanda are not here still, correct? I always want to make sure I have that right. Okay. I don't answer yet. Apparently opened the wrong one. It's happened before. It all looks good until we get to the first question. Yeah, this is the right one. Okay, now you may start answering. Okay, I am going to I've got to fix some clickers. Somehow things gotten really messed up. I know I just went and changed James, and it still doesn't show what I changed. So that's why I spent time looking at it. The answers we got here were 21 people said C, and one person said ratio of change in length to original length. The physics definition of stress is what the 21 people said. So we got that. Stress is the force applied divided by the area on which it's applied. What is this one down here at the bottom that we had one person answer? That's the strain. Now I talked about, a typical person who's never taken a physics class and how they use these terms stress and strain. Strain is a result of the applied stress. So I like to think about things like my classmates in graduate school. I had one classmate who came to a test and she had all these sores on her face. And, I was like, she's got some terrible disease. It's like, what happened? Well, she had been studying and going like this while she was studying and ended up gouging her face while she was studying. Now that's what we call abnormal behavior, right? There was a stressor here. The stress was the stress of the test, putting psychological force on her brain. And the strain was the deviation it caused in her brain that made her gouge her face out. Now, what I found to be oddly humorous was she was dating another one of our classmates, and he had no eyebrows or eyelashes. What happened to you? Well, I was studying. Going like this until he pulled them all out. And this is where I remind you what a blessing it is that we have the Sabbath day. My classmates were studying at least 10 hours, 7 days a week. It's really, really hard on you psychologically. I did not study at all. From sundown Friday night to sundown Saturday night, I would have felt guilty if I had studied. It helped me stay sane. I didn't do any of these crazy things. And I really do think God was wise in giving us this Sabbath, this time of rest and rejuvenation of the body, a time when we can avoid going crazy, which is what happens apparently in physics grad school to approximately 20% of the class. And many of you will be going to other schools where there's a lot of stress, and you need to be able to handle it and not damage yourself. Okay, now to circular motion. We have circular motion all the time. Here's an example. I have a little turntable. I rotate it. It's going to circle. Everything on here takes the same amount of time to do one complete circle. But the speeds aren't the same. If I have something that is close to the center and something that's far from the center and I spin them around, they both take the same amount of time to do one circle. But which circle has the bigger circumference? The one that's farther away or the one that's closer? Farther away. So that means the one that's farther away must also be traveling faster. So if we're dealing with something that is uniform rotation, that is, we have a rigid object that's rotating, it's often very convenient to talk about what's the same about them. And what's the same about these is the time that it takes to do a rotation. So we're going to start talking about that kind of idea today. One of the first things we need to deal with is angles. Notice in this picture, it doesn't have it completed, but the angles come here to the center, and they're measured going counterclockwise. This once again has to do with using right-hand coordinates. Counterclockwise is positive. So the convention is when you measure an angle, measure counterclockwise, and that's a positive angle. If you measure clockwise, that would be a negative angle. You notice I got my right hand and I curve it because in my brain I'm going through it's right and left. And so let's go through that. How many people know a mnemonic for how to determine which direction to screw in a screw? Righty-tighty. Okay, righty-tighty, lefty-loosey. That righty-tighty, lefty-loosey is a statement of the right-hand rule. The right-hand rule in its more exact statement for using a screw, screws have right-hand threads. The more exact is, if you turn it and use your fingers of your right hand to go the direction it's rotating. So if I have a screw that's vertical and I go like this, so looking down, that's a clockwise rotation, it's going to go the direction my right thumb points. So it's going to go down. If I put it so it's going counterclockwise, my thumb points up, it's going to come out. That's why we call them right-hand threads. And our convention is, if you take your right hand and put your fingers the direction that the angle is going, if your thumb goes up, that's positive. If it goes down, that's negative. Or coming out of the wall is positive, going into the wall is negative. So you look at the second hand is going like that. My thumb goes into the wall, and hence it's negative. Would have been easier to go like this, but then I couldn't see it. So that's our sign convention for angles. And we're going to use the right hand a number of different places in physics. It's a convention tool. It's a way to make sure we keep our number sign, our positives and negatives correct as we go through problems. Go faster. Arc length. I know that we're not all right up to date on studying things like circular motion. And so if we have a circle, an arc is the term for a piece of the circle. So in that picture, the green piece is an arc. And the arc length is written here as delta S. Why delta? Because in some time delta t, we've had something rotate through an angle delta r, and I'm going to go ahead and put an arrow to indicate that direction to make it a positive, or delta theta, excuse me. Theta, that's the Greek letter th. We traditionally use theta to measure angles. We also will often use this one, which to us would be F. And I learned to pronounce it phi. A lot of people pronounce it phi. Very few people pronounce it pho or fum. It is also used very often for angles. So those are the two most common angle variables we'll use. So this here, when I say delta theta, in my head, I'm saying just the change in angle, because theta to me is the variable for angle. Just like delta x would be change in position. So if we look at this circle, we have a mathematical relationship that defines the angle based on the arc length. The change in angle, the angle that it's gone through, is equal to the change in arc length, the arc length that's gone through, divided by the radius. This equation is actually one that you know well. Well, I say you know well. Let me go a step further. If you do a complete circle, what do we call the arc length for a complete circle? Circumference. So for a complete circle, change colors for the complete circle. Delta S is equal to the circumference, which is 2 pi times the radius. So if I put that into my equation for the angle for a complete circle, I have 2 pi. If I look at this 2 pi r over r, the r's cancel. I have 2 pi. What kind of units do I have? I know Michael knows because we talked about it. What do I have for units? I got nada. There are no units. This is a unitless angle. Now, through most of your lives when you measured angles, what did you use to measure angle? Degrees. You measure in degrees because, well, scientists have long known that there's somewhere close to 365 days in a year. And it's 365.2422 mean solar days in a year. 365 isn't a pretty number. I'm sure it's divisible by 5, but you know, it's not pretty. Whereas they said 360 degrees, that is an awesome, pretty number. Because 360 is divisible by 1, 2, 3, 4, 5, 6, you do have to skip 7, 8, 9, 10, you got to skip 11, and 12. It's divisible by all but 2 numbers between 1 and 12, and they thought there must be some real power and beauty in a number that's divisible by so many things. It's so easy to work with. And so they said, instead of saying that it's 365 days in a year, let's approximate to 360 days in a year. Now, they didn't do this on the calendars, but they did for measuring how much stars moved per day. So the motion seen, like if you were to go out at noon and try to observe where something is in the sky, you would see that they all move, or go out at midnight. It's a lot easier to see things in the sky. If you were to go out at midnight, you would see everything moves by what they call 1 degree per night. Now that's off by 5 out of 360. But that's where it comes from. So 360 degrees was just a way of taking the motion of the sky from night to night and putting that into a circle. So we use these 360 degrees, but we just showed here that the angle is unitless. So degrees must really be unitless, but it's a conversion factor of unitless from the unitless value. That's confusing, right? And so that's why we tend to call this radians, RAD for short, for the units. The radian is the word that means this is the natural unitless angle. And if I show something like degrees, that means I did a conversion factor I'm going to have to reverse. So radians will appear and disappear in calculations because they simply are saying we use the natural unit for angle. Whereas degrees can't appear and disappear, you would have to do something like convert it to radians to make it disappear. So how do we convert between radians and degrees? Let's do cycle, degree, and radian. So in one cycle, how many degrees are there? 360 degrees. And how many radians? 2 pi. So all of those have to be equal, so your conversion factors would be something like 360 degrees per 2 pi. Or if you want to go the other way. And so you can convert back and forth just using that relationship. That for a complete circle it's 360 degrees, or it's 2 pi radians. I'll put the rad there so we're clear on what I'm doing. And so that's all we have to do to convert angles. So you can do any old random conversion. Let's do ones we can do in our head. How many radians is 30 degrees? What do I have to multiply it by? 2 pi radians divided by 360 degrees. My degrees will cancel now. 3 divided by 36 is 12, so this is going to be 2/12 pi, or as I heard somebody correctly say, pi over 6 radians. Now I chose one that I could do in my head so I wouldn't have to whip out the calculator. Right? If I had said, okay, so what is 72.93 degrees? Obviously, I'd gone to the calculator there. So conversion of the units, not a big deal. The units that you use, you need to be aware of. You need to make sure if you're using things like sine and cosine, that the units you're using for angle match what your calculator has for its units of angle, or you'll just get wrong answers and you'll be like, but I punched everything in correctly. You did. If you have the wrong units in the calculator, it can't do it, right? Do you have a question, or is that... Okay, question number 2. Bob sits a distance r from the axis of rotation, and Ann sits a distance 2r from the same axis of rotation on a rotating merry-go-round. How do their speeds compare? Do they have the same speed? Is Bob moving twice as fast? Is Ann moving twice as fast? Bob moving 4 times as fast? Or Ann moving 4 times as fast? Okay, I'm going to stop it now. People are still changing their answers, oddly enough. Okay, so what we have right now is 3, 5, 7, 0, 6. Okay, get together with your nearest compatriots. So, like, Cassie, go ahead and turn around and talk to the young lady who didn't want to distract you. And James and Jeremy. And discuss what you answered, why you answered, what you think might be correct or wrong. Yeah.
Where it's just like someone trying to get a right or not.
It looks like more animated discussions have ended, so let's re-poll this and see if we have better consensus or worse consensus or the same. Okay, so it's now available for re-voting. Go ahead and cast a second. Okay, everybody who answered the first time has answered now, so we got rid of this when nobody said they have the same speed anymore. So we had a general convergence toward and is moving twice as fast. Now that's the correct answer, and let's look at why it's the correct answer. If we have two people at R1 is 1/2 of R2, then we look at, for a portion of a circle, they've both done the same angle in the same amount of time. But how do their distances compare? Since delta theta is equal to delta S1 over R1, or delta S2 over R2, I can say, well, right, I just substituted this equation. Since delta theta is equal to delta theta, I set them equal to each other, and I divided by delta t. But if I divide by delta t, delta S1 over delta t is equal to speed 1. And delta S2 over delta t is equal to speed 2. So my relationship is delta theta over delta, that's a, when you put it on the calculator, you type a Q. And my brain, or not a calculator, but on a computer, you type a Q. My brain went there. So the speed divided by the radius is the same for both of them. So in our picture, Ann would have been speed 2. So if I solve this for speed 2, V2 is equal to V1 over R1 multiplied by R2. Right? Just taking, change color, taking the things, oh man. Sometimes I don't remember what I'm doing. Taking things in that box and solving it for V2, I have this equation here. So V2 is equal to V1, speed of Ann is the speed of Bob, times the radius for Ann divided by the radius for Bob. Since Ann was 2 times the radius of Bob, she had twice his speed. So I can work this out with nothing tricky, nothing actually new, just using that relationship between angle and the arc length. But now there is something new to be learned here. What was that?
Is that a V1?
This is a V1, yes. That make it better? This thing, the change in angle divided by change in time, we give it a name. V was what we give for speed or velocity if it's a vector. For rotation, this is the rate of rotation, right? It's the rate at which the angle is changing. And the rate of rotation we call the angular velocity if it's a vector, or angular speed if it's a scalar, and we give it the symbol omega. The last letter of the alphabet, I think I mentioned before, it's lowercase. There are uppercase and lowercase Greek letters. Even if you know what the uppercase omega is, this is the correct lowercase. I had a student that corrected me once trying to say that that wasn't omega because she didn't know that there were lower cases. She was in a sorority and they made her memorize the Greek alphabet and that wasn't in it. So coming back to this symbol omega, it looks like a W to us, right? But it's got rounded bottoms. That omega is the angular velocity or the angular speed. Now, with velocity, it's pretty simple. What direction is my velocity? Well, it's whatever direction I'm going. So right now my velocity is like that. With angular velocity, it's a little more confusing. If I take this turntable and I make it rotate, any portion of that turntable has a velocity direction that's constantly changing. Now the velocity is always staying horizontal, but it's constantly changing. So if it's said, how do we get a direction for the rotation? They said, well, we can't take something horizontal because it's going through all of the different options for horizontal. If we choose one, it's meaningless. So it has to be something that's perpendicular to the horizontal here, which means either up or down. So you have two choices. And how do you suppose physicists settled that choice? With the right hand. If you wrap your fingers the direction it's rotating, your thumb is the direction assigned to the velocity. So the angular velocity now is going up. If I rotate the other way, now the angular velocity is going down. So the angular velocity has a direction, and you determine it with that right-hand rule. Now to put it into something practical. Our automobiles have tires on them. Drive down the road, that tire is turning, and so that tire has a certain angular velocity or angular speed. Remember the differences if you're using a vector or not. And the car has a certain speed or velocity as it's going down the road. And the question is, how do those two relate? Well, you can view the Earth here as if it's traveling with a speed v relative to that tire. So relative to the center of the tire, it's traveling at speed v. Well, we just learned our relationship that was omega is equal to v over r, or v is equal to omega r. So if I know the angular velocity, omega, for that tire's rotation, then I can calculate v, the speed at which the ground is moving with respect to the center of the tire. And of course, if the ground is moving at speed v with respect to the center of the tire, then I can just reverse my reference frames and say, well, with respect to the earth, the car is moving forward with speed equal v equals omega r. So you can equally or easily translate back and forth between the speed at which a car is traveling and the angular velocity at which the tires are rotating. But notice it depends on the radius. So your car has a speedometer. How does the speedometer measure your speed? Yeah, it's actually measuring omega. And then it's calculating the speed with that equation. So what happens if you have a flat tire? What's the speed going to be? Too high or too low? That is the speed your speedometer says compared to reality. If it's a flat tire, what's happening to R? It's smaller. And so what happens to your actual speed compared to what the speedometer says? It drops. So if your tires are flat, you're actually not going to be going as fast as your speedometer says. If you overinflate, you might be going a little bit faster. Or, your car says, you want, 22 R17s, and you say, but I can get, okay, don't be stupid. Don't change the rim size. Don't change the R number. That doesn't work out. But let's say you say, oh man, I could put on some 24 with the same R. A bigger tire. It'll still fit. It won't rub, hopefully. You put on a bigger tire, a bigger radius for that tire, what's going to happen? You're going to be going faster than the speedometer says. You get pulled over and you say, my speedometer said I wasn't speeding. That's really not a valid excuse if you put on the wrong tires. It's actually only a valid excuse if you've had it very recently calibrated. In most situations, it's not a valid excuse, which is sad. Yeah?
I didn't really catch that right-hand rule that you were talking about just a second ago, and I guess after that example, I realized I didn't understand what you said.
Okay.
The velocity is coming out of
the angular velocity.
Angular velocity.
So if I take this thing that's rotating, right now it's rotating like this. So I take my right hand and I wrap my fingers in the direction it's rotating. And then my thumb points down, so the angular velocity is pointing down. No actual velocity, linear velocity vector is pointing down, but the angular velocity is pointing down.
Okay. The linear velocity vector is still tangent.
The linear velocity vector is going around like this in a circle.
Okay.
Oh, shoot. No, I wanted to be on that slide. We'll stop with this slide. If you have something going in a circle, you have a constant change in direction, but it requires an acceleration to change the direction of motion. And so that change in direction necessary to go in a circle is called the centripetal acceleration. And I will pick up next class period with centripetal acceleration.